Hello everyone and welcome to Lesson 1 of Unit 6, Introduction to Sinusoidal Functions. In this unit, we're going to learn about a new type of function. This lesson will be devoted to studying the properties of that function. Here we go. Previously, you have seen the primary trigonometric ratios, in other words, sine, cosine, and tangent. And we use this in the context of calculating angles and sides in right angle triangles. But what we're going to do today is explore what these functions actually look like when you plot their points on a grid. Part 1 is going to involve the sine function, which is just f of x equals sine of x. To get us started, we'll complete the table of values below. So using a calculator, please evaluate the sine of each of the angles. To make things easier for us, we'll round all of our answers to one decimal place. This would be a good time to pause the video, work those values out, and when you're ready, click play to resume. Okay, so hopefully you got these values as well. Remember, we're rounding everything to one decimal place. And now let's see what this graph actually looks like. So on the grid below, please plot the following points. You'll plot the x values on the horizontal axis, and on the y-axis you'll plot the values of sine x. Once again, this would be a good time to pause the video, and when you're ready, click play to resume. Okay, and hopefully your points look like this. And what I'll do now is draw a curve of best fit through all the points. So this is what our sine function looks like. All right, and there you have it. That's the graph of y equals sine x. And now I'll answer some questions about it. First question, what is the domain of the sine function? Recall, when we're finding the domain of a function, what we're really doing is asking ourselves, are there any values of the independent variable that we can't substitute? And my general hint to you was to try substituting 0, any positive angle, and any negative angle just to see what works and what doesn't work. But on the previous page, we saw that sine of 0 was 0. The sine of any positive angle will return a number. And maybe just to convince yourself that it works, try taking the sine of a negative angle. Like for example, let's say the sine of negative 30 degrees. Doing so, you'll get negative 0.5. And I hope this convinces you that all negative angles work, all positive angles work, and even 0 works. So therefore, the domain of the sine function is the set of all real numbers. In part 2, we'll determine the range of the function. And I'll use the graph to help us do this. I'd like you to recognize that all of the y values are somewhere between positive 1 and negative 1. We see from the points that we've plotted, the y values are never going to get larger than positive 1, and they're never going to get smaller than negative 1. But both 1 and negative 1 are included. So therefore, the range would be the set of numbers. So therefore, the range would be the set of real numbers such that y is between negative 1 and positive 1. Okay, in part 3, we're going to relate what we just did to the cast rule from the previous unit. First things first, let's use our cast rule to find all possible angles such that the sine of theta equals a half, where theta is between 0 and 360 degrees. So let's review what we did last unit. I'll begin by labeling the graph first. So the sine of which angle gives you a half? Think back to the two special triangles that we drew last unit. And I hope you remember it must be the 30, 60, 90 triangle. So what we see is that when you take the sine of 30 degrees, it gives you exactly a half. So I hope this tells you that theta must be 30 degrees. And furthermore, I'd also like you to recognize that this ratio is specifically positive. So which two quadrants is sine positive in? Well, according to the cast rule, sine is positive in quadrants 1 and 2. So we have to construct two triangles with angles of 30 degrees. Let me demonstrate. But finally, we have to express the angles as positive counterclockwise angles. So what we see is when we're in quadrant 1, the angle must be 30 degrees. And when we're in quadrant 2, the principal angle would be 180 minus 30, or 150 degrees. Okay, so that was a review of last unit, and in question 4, you'll see how we tie it all together. This question is asking us to draw a horizontal line through y equals 0.5, and then determine which x values produce this y value. So let's do that. So we have to draw a horizontal line through y equals 0.5. And visually, where does that horizontal line cross the sine function? Well, I see two locations, one is here and the other is here. What x values do those occur at? Well, I think you'll see one of them appears to be 30 degrees, and the other one appears to be 150 degrees. That's exactly what we determined in the previous question. So let me just use this opportunity to mention something. Do you see the cast rule on this graph? Remember, sine was positive in quadrants 1 and 2. That included 0 up to 180 degrees. So where are 0 and 180 degrees on the graph? 0 starts here, 180 degrees is here, and notice between 0 and 180, all of the y values are above the x-axis. In other words, they're positive. Similarly, look at 180 and 360. That corresponds to quadrants 3 and 4. And you'll see that all of the y values for the sine function are negative. They're below the x-axis. So this graph is actually another visual representation of the cast rule. Okay, so to answer this question, which x values produce a y value of 0.5? We'll say that y equals 0.5 when x equals 30 degrees or 150 degrees. This is consistent with the cast rule. All right, and that completes about half the lesson. In the second part, we're going to investigate the cosine function. By the way, in grade 11, we're just going to look at the sine and cosine function. In grade 12 advanced functions, you'll look at the tangent function, as well as the secant, cosecant, and cotangent functions. So to get us started, I'm going to ask you to again complete the table of values below for y equals cosine x. Once again, please round all of your answers to one decimal place. This would be a good time to pause the video, try it out, and when you're ready, click play to resume. Okay, so hopefully these are the y values that you got. And once again, let's plot them on the grid below. The horizontal axis represents the angles, and the vertical axis will represent cosine of those values. So once again, please take a moment to pause the video, plot those points, and when you're ready, click play to resume. Alright, so those are what the points look like. And now to complete this, let's draw a curve of best fit. And that, everyone, is your cosine function. So now we're going to answer a very similar set of questions. First things first, what's the domain of this function? So I'll repeat for clarity, which x values are you able to substitute into the function? We just saw that we can substitute 0. We also can substitute any positive angle. But let's just test it out with a negative angle. So for example, if we worked out the cosine of negative 60 degrees, on your calculator, that's going to return positive 0.5. And I just wanted to demonstrate that you are able to substitute negative angles as well. So once again, the domain of the cosine function is the set of all real numbers. In question 2, to answer the range, we're going to look at the graph on the previous page again. And it's actually the exact same behavior that we saw for the sine function. So please notice that all of the y values occur between positive 1 and negative 1. They never get larger than 1 and they never get smaller than negative 1. So therefore, the range is the set of real numbers such that y is between 1 and negative 1. Okay, next question is very similar to before. We're going to use the cast rule to find all possible angles such that the cosine of that angle produces negative a half. So please again recognize the sign. This is negative. And as before, we're only looking between 0 and 360 degrees. So as before, let's begin by labeling the graph. So which of the two special triangles contain the ratio of 1 over 2? Once again, it's our 30, 60, 90 triangle. So the angle in this case that produces the desired result is 60 degrees. That's because when you take the cosine of 60, you get a half. But the ratio is negative. Which quadrants is cosine negative in? According to the cast rule, it's quadrants 2 and 3. So as before, we're going to construct two right-angled triangles where the related acute angle is 60 degrees. Okay, and just to remind you, we have to express these as positive counterclockwise angles. So how far do we rotate the initial arm to get to the location in quadrants 2 and 3? When we're in quadrant 2, the angle would be 180 minus 60, or 120 degrees. And when we're in quadrant 3, the angle would be 180 plus 60, or 240 degrees. Question 4 is very similar. We're going to draw a horizontal line through y equals negative 0.5 and determine the x values that produce this result. So here's the horizontal line. Notice that it crosses the cosine function at 2 locations. One of them appears to be 120 degrees, and the other one appears to be 240 degrees. And once again, I'm going to ask you, do you see the cast rule here? So notice when we're between 0 and 90 degrees, the y values of the cosine function are above the x-axis. In other words, they're positive. And similarly, when we're between 270 and 360 degrees, the y values again are above the x-axis. But that corresponds with quadrants 1 and 4, which is where cosine is positive according to the cast rule. Similarly, the y values are negative between 90 and 270, and that corresponds to quadrants 2 and 3, which is where the cosine function is negative according to the cast rule. So I hope you see the cast rule in this graph as well. So y equals negative 0.5 when x equals 120 degrees or 240 degrees. And I'll just make a note again, this is consistent with the cast rule. Okay, and that's going to wrap up lesson 1 of unit 6. There's a worksheet on our course website. Please work on that to get some practice. Thanks for watching, everyone. See you in the next video.